So in the last few clips, we looked at work and how to compute work as a vector integral. But that's not the only application, of course, of integrating vector fields. So now we're going to look at circulation and flux. So suppose that C is a simple closed curve in the plane. So what does that mean? These are actually technical terms. So simple, this part, means no self-intersections. It doesn't cross itself. And then closed, this means, actually here, let me do it in a different color. This part means that it ends where it begins. So you can start from anywhere, but your parameterization should have the property that your endpoint, C of B, should equal your starting point, C of A. So in other words, if we have something like this is a curve that is not simple because it intersects itself right here in the middle. If we have a curve that looks like this, then this one is not closed because there's a gap between those 2 points right there. So we're talking about something that looks like this, or something that looks like this, or something that just looks like a circle. Okay, so simple closed curves. All right, so let's see. So now, if F gives the velocity of a fluid moving through the region, then the circulation is the work done along the curve, and the flux is the flow across the curve. And so the idea here is that when I say along, I mean that we're looking at it going parallel to the tangent of the curve, and tangent. And when I say across, I mean transverse motion. So it's going to be orthogonal to the tangent. So circulation is, so this is just going to be work. So it's going to be P dx plus Q dy if we have a vector field with components P and Q, right? And then because it's a closed curve, it's common to put a little circle on the integral sign. And sometimes you'll find books that actually write it like this with a little arrow to indicate that the circle is moving around counterclockwise. Okay, so circulation, we've actually just done several examples of, well, I guess the path might not have been closed, so I shouldn't say that it was circulation. But formally, the computation's exactly done like the examples we just did. However, flux is something new and different. So for flux, what we're doing is we're going across the curve. So this means now that instead of going parallel, we're going to be dotting not with the tangent to the curve, but instead with the normal vector. And that'll also be denoted with a little circle because we've got a closed curve here. And so this let me just N here is the unit normal vector, and it is in fact the outward unit normal vector. So just going back over here to this curve right here, if I were to draw the outward pointing unit normal vector, it would be length 1, length 1, length 1, length 1. These are the outward pointing unit normal vectors to the curve at various points along the curve. And if I've drawn it correctly, each of these should be orthogonal. I don't know if I really managed that right here. But here, maybe I'll do some, okay, orthogonal on the other one as well. Here, 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 here. You get the picture. Okay, so outward as opposed to inward. We don't do that one. So it's an orientation convention that we always have it pointing outward. Okay. And so F dot N so this is the projection onto the normal to the curve, is the component of f which is orthogonal to the curve. Okay, so how are we going to get our grubby little mitts on this piece of the puzzle? So, by the way, if this is our curve and this is our vector field, just to make life easier, I'll take a vector field which is like constant or always pointing in the same direction here. Okay, so if we are at some given point, let's see what's a good point to do this at. How about like right here? Okay, then the tangent is going to be going this way. So there's our C prime, and there's going to be our vector field, and there's going to be our unit normal. And so the vector, the force field, is going to break down into orthogonal pieces. One part which is going straight across, that's going to be where you get flux. One part that's going parallel, that's where you get the circulation. So when we look at circulation or flux, we're just asking which part of the vector field do we care about? Do we care about the part of the vector field that's going along the curve, or the part of the vector field that's going transversely across the vector field? Okay, so to get our mitts on this, let's see, if C is counterclockwise traversed, which is our standard positive orientation, so we're going that way, then we can get our unit outward normal vector by doing a cheap trick. We consider R2 as the z equals 0 plane in R3. That'll allow us to use a cross product. So then we have n is going to be, we take the cross product between t, our tangent vector that we found before, and k, the unit vertical. So that's the one that's going in the direction of the z-axis, right? So let's see, so what does n look like? Well, in terms of coordinates, it's dx, ds, and then, well, we can write it actually as a sum. So it'd be I hat plus dy, ds, j hat. And then we're gonna take the cross with the k vector. And if you work out what that cross product is, you find that it's dy, ds, I hat minus dx, ds, j hat. Okay. So if our force field has components P and Q, wow, that was terrible, Q, then the dot product of F with N is going to be P times dy ds minus Q times dx ds. And then we have that the flux is the closed integral over C of f dot n ds, right? That's what we agreed back upon the beginning. And so now writing this in terms of components, we have p dy over ds minus q dx over ds. The ds in the denominator, remember that's from normalizing, so that the tangent vector is a unit tangent vector. And just like it did before, we see that it cancels with the ds on the outside. So we end up with the flux integral just being p dy minus q dx. So that's cute. So that's the one that we will keep in mind when doing calculations.